This talk's been put together based on work I did with Graham Gansel, who's our data science lead. And it covers something we've been researching over the last 9 months, which is graph convolutional networks. Now, we started looking at 9 months ago, particularly the problem of if you have a lot of data in a graph, how do you get most of that data in to some type of deep learning architecture? Because in general, deep learning architectures aren't set up to process graphs. They like regular structures. They like to work on matrices and vectors. So we started looking around, doing some research, and found various ways that people were trying to fit the two together. And we came across a very nice architecture that we've used and applied to one data set as far as this talk is concerned. And what we'd like to do is today I'm going to take us through why graph convolutional networks are needed, really. Why do you have to treat graph data differently? Some of the applications. And then I'm going to show some results. And then we can have a discussion off the back of that. So most of the talk is going to take us gently through the concepts. There's a bit of maths, and I've got a bit of a demo to run at the end. Okay? So, application areas for GCNs. The thing we're going to focus on is node classification. So just to be clear on that, let's say we have a graph data set where we're going to have properties on the nodes themselves. We're also going to have properties on the edges. A classification problem is to add a label or an additional property across all the nodes in that graph. Now, typically, if we've got a data set that we're using for training, then at least some percentage of those nodes are already going to be labeled. In that case, you can think of this as a label propagation. You want to use the properties in the nodes themselves plus the relationships in the graph to decide how to propagate those labels out over the graph. It turns out this is good in a variety of application areas, from semi-supervised learning. And so semi-supervised learning, where potentially you don't have a lot of training data yourself. This is a technique that can cope with small amounts of training data. And it's also very useful, of course, when the data you're dealing with is naturally a graph. So just as an example of something we might do, if you take this is a well-known Facebook data set of just a network expanded around a single node, so the ego network of someone. And one way to analyze this from a graph analysis point of view is to cluster it. So take some measure. For example, you might decide that some set of attributes lines up with somebody's political stance. So then you would sort of create a cost function cluster based on that. And on the right-hand side, you've got a force directive graph where the edges are showing the inverse of that quantity, and we can sort of push apart. And it's very effective visually to show where the concentrations and the different communities of different political stance are in the data set. And that works really well visually, but again, what we want to try and do is have a neural network do that. So whenever we think clustering on a graph, there's potentially a node classification approach with a deep learning system. Here we've got sort of grades of we've got a color bar in play here, which of course would be sort of a regression problem, but we could easily imagine that we've got different categories which we're going to classify into. So that's one particular application area. Another thing that these things can do is they can work with subgraphs equally as well. So if you imagine we have some network of people, and around each people, if we can call these things, for example, supernodes, so the nodes in here are individuals, then each individual might have a subgraph associated with them, for example, all the transactions. And if we can train on those subgraphs, known fraudulent and non-fraudulent ones, then GCNs can start encoding that information into the network in order to then do prediction or classification. So they are really cool things. So just beyond the node classification, we're not going to talk about much today. You can actually get these things to produce graphs. So you can have graph networking in the form of you'll see later, in the form of sort of adjacency matrix data. And what you'll get out is another graph representation where the structure has been updated. So you can use it to cut graph edges. You can use it to predict new links in the graph. And there's plenty of papers out there doing that. And specifically, there's some that take the autoencoder type of architecture and then apply that using graph convolutional layers as well, quite effectively. So, but why not just use a CNN? And again, there's a whole spectrum of research out there. People have been trying everything with graph data, including shunting it into CNNs. And I want to talk a little bit why that isn't a bad idea. Sorry, why that's a bad idea. But at the same time, CNNs have some great properties that we want to be able to leverage in GCNs. And it's worth exploring those a little bit. So, by the way, just hands up, who all have sort of ML backgrounds in the room? Okay. This is going to be a little bit 101-ish to start with, but just to sort of level set for everyone. So, one of the biggest activities when you're trying to use a neural network is feature engineering, or any type of machine learning model. You're trying to build up some type of feature space that you can use to represent the salient information within the data set. For example, credit approval prediction, you might bring in attributes like age, gender. You might bring in a lot about employment and end up building this large multi-dimensional feature vector. And these things tend to get quite large, they tend to get quite sparse, and you can spend a fair amount of time tuning your model by selecting which features and deciding how to pre-process those. The simplest type of neural network, of course, is a simple feed-forward or multi-layer perceptron. There we've got a neural network with multiple layers, usually all fully connected, and we're using it to make some classification, so a binary classification decision based on that feature vector. These are great because they encode relationships, and they're extremely powerful on general feature data. But they aren't so great where you want to start encoding any type of spatial or temporal relationship that's inherent in the data set. So then we move to convolution. That's a little convolution GIF there. And of course, convolution is some type of operator, usually around a local point, that allows us to soak up and sample information relative to a current sample in the signal. It works for images in a multi-dimensional sense. So we can do up to ND convolution and convolve on any sort of dimensionality data that we like. The analogy is that you have this sliding window that moves across your data set in order to apply a filter, then produce a coefficient in the next level. And the CNN architecture actually reflects that. So every point of the sliding window will be a position or a neuron output in one of the feature map layers. And then typically you have quite a deep CNN structure with multiple layers. Each sampling, there's usually some subsampling or pooling, followed by convolutions, until the end you get something that again looked like the MLP, which is some type of fully connected network layer that takes this sort of resulting latent space and maps it to your output classes. So what you can think of is this is all representational. This is all about breaking down the input signal through various levels of representations so that you get a compact compact feature vector at the end that you can then map. And that's really where all the learning happens relative to your problem in the final layer. So why is this so important? It's about the type of information that those are code. This is quite. We've seen pictures like this before. There's plenty of them in the literature, and it's the idea that early on in the neural network, the first convolutional layers tend to learn simple image processing operators. If you look at image processing textbooks, you'll see operators like this for edge detection and texture characterization and stuff. And then as you go down the network, the layers start to capture more and more of the input data, and moving towards higher and higher level of abstractions. And that's something that we would love to apply to the graph, because what that means is by setting up a convolutional network on a graph, you're able to take small local measurements, but then as you add further layers in, you're actually reaching out and taking a new version of Java. You're actually reaching out and taking bigger abstractions and bigger glances across your graph. So you end up encoding into the neural network large swathes of your graph structure in the same way here as we encode faces in deeper layers. And that's why I think the GCNs are uniquely powerful over some of the other methods that are used to squeeze graph data in. So graphs. Graphs are... This is a sort of split graph ML conference, so the other half of the room is all experienced people with graphs, perhaps? Or a couple, yeah, okay. So 101 on the other side now. So small chemical graph, or like that, which might be good for a graph matching problem if you have many of them. That's like subgraph matching and pattern matching across a larger data set of smaller graphs. But a lot of time as well, we have a bigger graph that we want to classify on, for example, do node classification on a large network. And a good way of thinking about it is one of the reasons why this is so difficult for a CNN or ML architecture is because nodes and graphs are only positioned relative to themselves. There is no inherent grid. There is no inherent spatial relationship. So how do we start to define an operator like convolution on a graph? It is ill-defined because distances between nodes might be different. You've got irregular sampling, and then it doesn't really mean anything. For example, what does a graph with a disconnected subgraph in it, or a loop back to a node mean? Those things introduce discontinuities in the derivatives and discontinuities in the space that means we need a very different approach. So I've seen quite a few papers like this that take the feature building approach to graphs, and some of them get quite sophisticated. They'll pull in node properties. They'll pull in node properties from individual nodes. They'll actually go and do some graph analytics and compute some extra data about the network to try and again bring in some of this relationship for information from the network. And for example, they might do clustering. They might do degree centrality or betweenness and use those resulting labels and quantities on the nodes to build another section of the feature vector. And then some techniques actually do subnetwork or random walks around nodes again to generate stuff that they can pack into feature vectors. And the problem is that these feature vectors get extremely large, they're sparse, and people put forward reasonable results, but it always seems there should be a better way to capture the information. So now we start on what GCNs are leveraging, if you like, in the graph, because the graphs at the end of the day can be represented by their adjacency matrix completely. So if we think a little bit about adjacency matrices, they obviously grow with the size of the graph. 4 nodes, that's this graph down here. It's quite a sort of manageable amount, and we keep getting larger and larger and larger matrices as we move to larger networks. And maybe you can start to see already some of the problems that we've got with the matrices. There's a sort of non-uniqueness there in terms of the adjacency matrix doesn't really care about how we label our nodes or anything. It's completely dependent on that. It's only encoding structure. So we can't use the adjacency matrix on its own. We need adjacency matrix plus information about the nodes, which is something we can cope with maybe. But things like cyclic permutations, these are the same graphs, but we have very different adjacency matrices. And then small perturbations in the actual network itself. So we've actually changed one value here, but because adjacency is always symmetric, we have 2 pixels changing. So imagine changing this as an image. It's very, very susceptible to noise. Any small change, 1 pixel in an image would be acceptable. Here, that's going to dramatically change the structure of our network as well, which is going to dramatically affect the results if we were trying to use a normal convolutional network. So people have tried again to use adjacency matrices directly as images, but it's the size of them, the spatial organization. This is the les mesurables. My French is terrible. Data set. I think it's it's frequency. The graph is of frequencies between character occurrences in the same scene, and this is order by name, order by cluster, order by frequency. It's all the same graph. Yet the spatial layout bears no resemblance in any of those 3, so you don't have any spatial correlation that's actually meaningful for your images. Plus, they get incredibly sparse, which is wasteful if you're going to use an image-based CNN for it. So the trick behind all of this stuff is something called graph embedding. Embeddings are well known, but embedding is any time we take a feature vector and we reduce it. So anytime we go from 100 dimensions down to 10. So that's using PCA in the simplest, but then kernel PCA or autoencoders to compute latent spaces and all that type of thing is all generating an embedding, which is a nice compact representation. So what we want to be able to do is do that with our graph. So quick example, we've got a weighted undirected graph, and that's its adjacency matrix. And what we want to do is, imagine that's the graph. Sorry, I've moved my slides back and forward. Imagine that's the graph. What we want to be able to do is create this latent space, a lot like PCA does, principal component 1, principal component 2, that is regular, and it still contains, say, 90% of the information from our graph, but the actual layout of the nodes in here is somehow respects the distribution in the graph. So we've still managed to encode some percentage of the graph structure, and then that's a successful embedding. And this is another technique that people are using, and it turns out, luckily, that that's very well established. A graph spectrum is a well-known graph theory technique where all we need to do is take our adjacency matrix, take the degree matrix, which is this one, just the number of connections into one node, and then we can compute the Laplacian, and then we solve it for its eigensystem using some library, and there we then we have the graph spectrum. So we have a spatially independent, rotation invariant representation of our graph that we can then play with, and the graph spectrum is a very good basis for the embedding. So here the spectrum itself is actually called the eigenvalues, so that's a bit like the Fourier coefficients, and then the structural matrix is a bit like the Fourier transform. So what people do, and this is a perfectly good approach, I've seen some very convincing results using this approach, is you do dimensionality reduction and decide to make your own node embedding space just by selecting columns. So in reality, maybe this is going to be the dimension of your node, the dimension of your adjacency matrix. So that might be 100 by 100. You might select the first 10 where most of the energy is, because you might find that these peter off after 10. Then you've actually got the majority of your graph structure, and you could use that and actually get structure of the network embedded in straight away alongside your other data in feature vectors, and that would be pretty successful using the standard methods as well. The rows, incidentally, represent actual nodes in your network, so at any point in time you can find out the coordinates of those in the space. So very powerful. What people have tended to do beyond that, there's this concept of graph kernels, people trying to define different kernels operate on. Sorry. Does that mean you don't have to compute the eigensystem? You can take any orthogonal basis. Okay. Okay, no, I hadn't. Thank you. The next step through this flow was the graph kernel methods of, and I think there are multiple definitions of the how the spectrum is defined as well. We're able then to define convolution with an analog to the Fourier domain. So in a time domain signal, we have convolution here, which becomes immediately a simple multiplication of Fourier domain. So what happens to get a graph convolution is this is our eigenvector matrix. So this is essentially our Fourier transform. X here will be a vector of one property on each node across our network. So we're able to, and these are our eigenvalues, we're able to compute convolutions immediately on any one node in the network. Problem is that's extremely expensive. So if you imagine a convolution which is just an inner product, multiplications and a sum, this becomes then very expensive to compute that eigen series and then compute the outer product. So GNNs in practice, we've been experimenting with one technique in particular, which is a guy out in the Netherlands. He's a doc student. He's done some very good work on simplifying the convolution equation. And some of his results have shown that you can get a long way with a first order approximation. So what he does is he uses a first order approximation, very like just taking the first order of a Taylor series expansion around the current point. So it works well, but it's it somewhat limits the receptive field, if you like, of the unit. And what we've got here is basically you have a weights matrix you initialize for the layer. This is the input. Now in the input layer, this will be nodes versus features. This is the adjacency in the degree matrix. The hat means it's been added to the identity matrix, which is one of the tricks he uses to get to that. And this is an activation function, relu or something. And then you can build up a multi-layer network using those as kernels, and then you've got a reasonable compute time, and you can actually do these things. This is very easy to set up in TensorFlow. We set it up, and for the purpose of this talk, we set up a 2-layer network, just with some dropout there. So there was two graph convolution layers, and then we did a softmax. It was straight out of the cross entropy loss, and we computed our two classes. I'm not going to go through that. So data sets. So I've got some results from 2 data sets here. The citation network, that was the same one as Kith used. We've been running that to make sure that our implementation was lining up with his results. But we also used the credit network. Now this was some of my colleagues, Lynn and Chris, presented this at 2 o'clock. So this is the US Census data. And what we're trying to do is use the network to predict whether somebody would get credit approval or not. So quite a chunky network, 45,000 nodes. By the time we'd construct our edges, we got about 9 million. And we picked 14 features from, I think, the 80 that's in the data set. And we're only aiming for 2 classes. So this is quite interesting, because this is one of the cases where this data is just rows. It's not naturally presented as a graph, But what we did is we decided to build a graph out of it by creating edges based on groupings of age and employment history. So we're taking a data set that might not automatically be a graph, and we're adding relation data to it in order to make a graph. And this is what we got out. So it took quite a bit of training still. The credit network, we trained that up on an MLP and on the GCN, and we achieved those accuracies. So the MLP, we got 62% accuracy, and the GCN we got 78, which doesn't beat the random forest that they used over 3 attributes. So we've got some explaining to do, yeah. And but the citation network that KIF used, we put that through our MLP as well, and also the GCN, and we got 81%, which we were quite happy with, because we're sort of agreeing with KIP's results from his published in his paper. So that was lined up that our code. Sorry? The data distribution, actually in the training data. I think that was roughly balanced. Yeah. So the actual training, the actual number of approved and no, it wasn't. No. Yeah. I can't remember the exact numbers. We'll see in a minute. The results at 78% accuracy were coming out at. Well, I've got a slide in a minute. It's got the numbers on, but no, it wasn't balanced. There was far more unapproved, and yeah. Okay, I'm not going to open TensorFlow because that'll take too long. But what's nice is these kernels, they're so small, they fit nicely into TensorFlow, and that's great. So deep learning demos don't always turn out to be the most exciting. Python. It gives me an excuse to talk about how we trained it. One interesting thing here is, so that's trained very quickly on this laptop on that, and that's on the very, very small Cora data set, and we've sort of got out hopefully about 81.4%. So how do you train these things? Because at the end of the day, you've got, in this case, we constructed a graph. We've got labels on every node, and what do you put in? What do you get out? So the graph, what you get out is you get a class versus node array. So in our case, 2 by n array of outputs, which you then have to paint back onto your adjacency matrix. Your inputs are nodes for features, and you're inputting the adjacency matrix at each step during the layer, so that's traveling independently through the network. So what we did is, because it's difficult to do sort of a cross-fold, like a sort of k-fold validation. So what we did here is we did that on the node labels only. So we masked out, I think, 20% of the labels, ran with 80%, trained, and then on one epoch we would validate, and then the next epoch we would select a different set, and so on until we completed all the epochs there, and then the network's trained, and then you can do a forward pass with test data. The interesting question, and it's still an open question, is what do you do to do proper k-fold on a graph? Because anytime you modify the network structure, you're fundamentally changing what you're mapping into the network layers. But yeah, so that's still an interesting open question of how you would do that, especially if you're processing a large network. One of our best answers at the minute is maybe find ways to split large networks by clustering out on features you don't think you're relative to, and generating multiple chaining sets, where in those clusters perhaps you still have the same patterns that are relative to what you're, which are interesting for what you're building. I was expecting a higher resolution screen. Oh, there you go. Good. So this is a little sort of workbench that we have to play around with some of our stuff in to explore these data sets. But we had we basically took all the nodes. It was impossible to render the edges. It would just grind the computer, took a halt. So we rendered all the nodes, and we've organized them radially. So going out is age, and on the spokes we decided to render number of hours worked per week. Just picking out two, and you can imagine. And then that was the full network. And then when you resolve out, they were the two classes. So we were actually predicting 30. So out of the 45k, the results came out at 87,000 unapproved and 8.5k approved. And obviously that's gross. We haven't done any breakouts into how many were in different categories, or where our true positives, etc. were. And then that's interesting, and then that's it. So, just conclusions-wise, this is the convolutional networks. I think once we discovered them, we've been obsessed with trying to use them for stuff, and I think that's the unique property that they have, is that the only things I've seen that fully encode graph structure without having to have somebody fiddling around, feature engineering and adding that extra human factor into trying to decide what levels to how to extract salient information about the network structure and use that. But I think they do still present some challenges. That was it. Thank you.